Hi everyone, welcome to the video lecture on goal programming models. For this video lecture, we're going to introduce the topic of goal programming, which is a part of chapter 6, integer goal programming and nonlinear programming. This is the second part of the chapter where we discuss an extension of a linear programming model by allowing for multiple objectives to be solved for in a single model. So in the reason why we need to cover goal programming and the reason why we needed goal programming as a technique is because in a business environment, usually just maximizing profit or minimizing cost, it is not the only objective that a firm may specify. In a lot of cases, maximizing profit is just one of the several objectives that may include maximizing, for example, machine utilization or maintaining full employment or providing quality ecological management or reducing the environmental damage of the production process from your business or minimizing noise levels in a neighborhood and similar other numerous non-economic targets that the businesses want to achieve in addition to maximizing profit or minimizing cost. So a lot of the times when we have multiple objectives, they tend to conflict with each other. So it may not be possible to simultaneously achieve these objectives, which is why we're going to learn the technique on goal programming because it helps us develop a decision model which can solve for multiple objectives in the same model that a regular LP model or an IP model does not do. So now the question arises, how is GP or goal programming modeling different from LP or IP? So the answer to that question is, in a regular LP model or an integer programming model, we try to find the best possible value for a single objective. That is, our aim is to optimize in a single measure. In GP, however, we first set a goal or a desired target for each objective. It allows for multiple objectives. In most decision modeling situations, some of these goals may be achievable only at the expense of the other goals. Therefore, we establish a hierarchy of rank or importance amongst these goals so that the lower ranked goals are given less prominence than the higher ranked goals. Based on this hierarchy, GP then attempts to reach a satisfactory level for each goal. The key word here is that in a GP, in a goal programming model, we try to satisfy the multiple objectives rather than optimizing them. So remember that in an LP model, we optimize, whereas in a GP model, we satisfies. Now, the next question that comes to mind is, how does GP satisfies the goals? So instead of trying to maximize or minimize the objective functions directly, like we do in a regular LP or IP model, with a GP model, we try to minimize deviations between the specified goals and what we can actually achieve for the multiple objectives within the given constraints or the requirements of the model. These deviations can either be positive or negative depending on whether we overachieve or underachieve a specific goal. These deviations are not only real decision variables in the GP model, but they're also the terms in the objective function. They're the only terms in the objective function. So the objective is to minimize some function of these deviation variables. So for example, think about your goal in this course. Let's say that you had a goal to get an 85 out of 100 in the midterm exam. Now, that is a goal that you have set for yourself. If in the actual midterm exam you end up getting 83, then you are underachieving the goal by 2 points. However, if you get an 87 or an 88, you are overachieving what the specified goal was. So this difference between what you actually achieve minus what the goal was is what we call the deviation terms. And we'll talk about these deviation terms in the context of a specific example just shortly. But for now, you have to understand what do we mean by these deviations. These deviations are by how much we overachieve or underachieve a specific goal. So if, for example, if you hit your goal at the exact target that you had set, then your deviation would simply be 0 because you've met your goal and you did not underachieve or overachieve. Like I mentioned earlier, in the GP model, we have to sort of prioritize or rank the multiple objectives or goals that we're going for. And there are two approaches of prioritizing your goals. The first approach is using a weighted model, and the second approach is using a ranked model. And we'll discuss an example for each of these two approaches to help you understand what I mean by each of these techniques. The first example that we're going to cover would be for a weighted goal programming model. And we're going to use the example of Wilson Doors Company. The full description of this example is given in the textbook under chapter 6, but just to give you a brief summary of what the problem at hand is, let's consider the product mix problem for Wilson Doors Company. The company manufactures 3 styles of doors, exterior, interior, and commercial. Now, each door requires a certain amount of steel and 2 separate production steps. You can see that in the table here. Steel is the first row in our resource availability table, and forming, which is a part of the production process, and assembly are the 2 other resources that are available and required for us to use to create these 3 products: exterior doors, interior doors, and commercial doors. So this table here shows the material requirement, forming and assembly times, as well as the selling price per unit of each product, along with the monthly availability of all the resources that you see in the last column. So for example, if I'm building 1 exterior door, it would require 4 pounds of steel per door. It would require 2 hours of forming, and it would require 2 hours of assembly. And I can sell this exterior door for $70. So we will go ahead and formulate our linear programming model just the way we've been doing for the rest of the problems under linear programming. We're going to use the selling price to set an objective function of maximizing total revenue or total sales. The decision variables are the number of doors to produce of each kind. So E, I, and C respectively refer to the exterior doors, interior doors, and commercial doors, and the quantity, how much to produce of each door. The objective is to maximize total sales. We're using the selling price given in the previous table as the objective function coefficients, subject to the resource availability constraints. The first one is for steel usage. The second one is for forming time. The third one is for assembly time. And then we have our regular non-negativity constraints. Now, all of this, I'm not going to repeat the model formulation process because we've covered this already. So I want to spend more time on the actual goal programming technique. Here, this is just your regular LP problem, which is the first step for us in order to understand the example on weighted approach to goal programming. Now, if you solve this particular model that we have created and you see in front of you on this slide here, the optimal solution of this LP turns out to be to produce 1,400 exterior doors, 800 interior doors, and no commercial doors for a total sales of 186,000. Now, at this stage, you should be able to easily verify this yourself by solving this in Excel solver. If you solve this specific model that we've created here, to maximize our total sales subject to these four constraints, the optimal solution that comes out for this particular LP problem tells us that we should be producing 1,400 exterior doors, 800 interior doors, and 0 commercial doors for a total sales of 186,000. Now, at this stage, you should be able to verify this yourself. However, the LP solution is going to be included in the Excel file that I have uploaded on Canvas. You can take a look at that for the solution for this particular model. However, once you look at the solution, let's assume that Wilson, the Chief Executive Officer of the company, is not happy with this LP solution because it generates no sales from commercial doors. In contrast, exterior doors generate most of the revenue. I'm going to switch my screen to the Excel solution for this LP problem so that you can look at the numbers. So solving the model as a regular LP model gives us this solution. Like I said, 1,400 exterior doors, 800 interior doors, and no commercial doors with a total revenue of $186,000. However, since Wilson is not happy with it because by producing 0 commercial doors means that they have to let go of all of their sales employees who sell commercial doors, which is not an option for them at this point. So instead, what Wilson wants to do is he wants to get a solution where we try to strive to get more than one goal achieved. And the multiple goals that he's looking for are formed using this original LP problem solution. So he knows that now the maximum profit that he can generate with his 3 products is $186,000. So the first goal that he wants to achieve is to have a total sales of at least 180. The reason why this target that he has set for his company or his business is lower than this maximum is because he knows that the additional constraints or the additional goals that he's trying to introduce to the model may restrict his ability to achieve this full revenue of 186. So he's willing to settle for slightly less revenue than what this LP solution suggests. The second goal that Wilson has set for his business is to achieve exterior door sales of at least $70,000. Now, currently, if we want to check what this LP solution gives the exterior door sales as, it would be the quantity multiplied by the selling price. And you can see here that the current LP solution is telling Wilson that the exterior door sales or revenue is 98,000. So he wants to set a goal or a target for his exterior door sales at least 70,000. I'll put that down here as well, just so that you remember the number. The third goal that he wants to achieve is have interior door sales at least $60,000. The current LP solution is giving him the interior doors revenue as 88,000. So the goal he set for his business based on this 88,000 is 60,000. And then finally, the fourth goal that he is set to achieve is to have commercial door sales of at least 35,000. We know that currently the LP solution is telling him to produce 0 sales from commercial doors, but the goal that he sets for himself is 35,000, just so that the salesmen for commercial doors don't have to be fired. Now, these three numbers here for the goal targets, think of them as arbitrary numbers. It doesn't matter how we got them out of these 98, 88, and 0, but think of them as targets which are set to be lower than the solution from your LP problem, because we all know that when we increase constraints and we increase restrictions, the ability to achieve all of those targets may not be there. So we want to set some achievable goals, which is why these targets are set as lower than what the LP solution is suggesting. So after solving the original LP problem, Wilson has now created a set of goals for his business that he would want to achieve. These goals are what you see on your screen right now, and we just went over them. Goal 1 is to achieve total sales of 180. Goal 2 is achieve individual exterior door sales of at least 70,000, interior door sales of at least 60,000, and commercial door sales of at least 35,000. Notice that these goals look somewhat similar to constraints. However, there's a difference between setting these requirements as goals instead of constraints. The difference is that constraints are restrictions that must be satisfied by the solution, whereas goals, on the other hand, are specifications that we would like to satisfy. However, it is acceptable to leave one or more goals unsatisfied in the final solution if it is impossible to satisfy all of them in the same model. So now we have a GP problem in which we want to find the product mix that achieves these 4 goals as much as possible given the production resource constraints. So remember that goals look similar to constraints, except that goals may remain unsatisfied in the final solution. That is an acceptable solution for us, even if the goals are not satisfied. However, constraints have to be fulfilled, otherwise our solution becomes infeasible, which is why we want to set these requirements as goals instead of constraints. So let's start our model formulation for the GP problem. In order to formulate this problem as a GP problem, we must first define 2 deviation variables for each of the 4 goals that were given in the previous slide. Now, as I mentioned earlier, deviation variables are variables that measure how far away from your target are you. So let's take a look again at the 4 goals. Let's take goal number 1, and we will call goal number 1 as the total sales goal. The total sales goal is to achieve total sales of at least $180,000. And if I go back to the deviation variables slide, I want you to focus on the first 2 deviation variables. The first deviation variable is labeled dt minus, and the second deviation variable is labeled dt plus. So for every goal in a GP model, we create 2 of these deviation variables. Sometimes we may even create single deviation variable depending on the situation, but normally we do create 2 deviation variables. And this is specific to the first goal. And we can denote that by this capital T here, which refers to total sales. So we know that D negative T and D positive D are the deviation variables associated with our first goal. And the way we define these 2 deviation variables is the first one, DT negative, is the amount by which the total sales goal is underachieved. we know that the target for total sales is set to 180,000. So if we end up making total sales of 175, then dt negative would be 5,000. Whereas dt positive is the amount by which the total sales goal is overachieved. So this is the case when you make more than what you had set as target. Let's say, for example, if you make 185,000, then you have overachieved your goal target by 5,000. If you hit your goal target exactly 180, then both of these deviation variables will have 0 values. Now, what you should also consider at this point is that if you have overachieved your goal, you will not underachieve it. And the same way, if you've underachieved your goal, you will not overachieve it. So only one of these two values will have a positive number value. The other one would automatically just be 0. The same way, we create two deviation variables for the remaining three goals. So d negative e and d positive e would be the deviation variables for our exterior door sales goal, which is goal number 2. D negative I and D positive I would be the deviation variables for our goal number 3, which is for interior door sales. And that's why the subscript is I. And then finally, for our fourth goal, which is the commercial door sales, D negative C and D positive C would be the associated deviation variables. Next, we're going to use the previously defined deviation variables to help express our goals as mathematical equations. So the first goal was the total sales goal, and the target was 180. So the total sales expression, which was also our original objective function for the LP model, 70e plus 110i plus 110c plus the negative deviation minus the positive deviation should be equal to 180,000. Now, notice that we've added the deviation variables in this equation to the left-hand side. The reason for that is by adding these deviation variables, we are allowing the left-hand side to have a value either greater than 180 or less than 180. So it's not like a constraint equation. Instead, by using these deviation variables, we are allowing our goal to be unmet or overmet by the certain amount that these deviation variables represent. The next question that comes to mind is, why is the negative deviation term added and the positive deviation term subtracted? The reason for that is if you have underachieved your goal, which means your negative deviation term would be a non-zero value, whereas dt positive would automatically just set to 0, then in that case, the fact that you did not achieve your goal means that you would have to add this deviation term to your expression for total sales just to get to the goal target of 180. So this is similar to saying if you set your midterm exam score to 85 out of 100, then if your actual score is 83, then you have to add the deviation variable of 2 to it to get to the goal of 85. So that's the reasoning behind adding the negative deviation and subtracting the positive deviation. The same way, goal number 2, defined mathematically as an equation using the deviation variables, is 70e plus the negative deviation for e minus the positive deviation for e has to be equal to 70,000. The same way we create the equations for the interior goal sales, which is goal number 3, and the commercial goal door sales, which is goal number 4. So in all of these here, these are the simple equations that we use to calculate total sales, except that now we've added these plus minus terms to it so that we can measure how off from the goal are we. Are we crossing the goal or are we under the goal target? And that's what these deviation terms will help us keep track of. So by using these deviation terms in our goal equations, we can now set our objective function as to minimize the total underachievement of goals. Because if we overachieve the goals, obviously that is going to be welcomed. So we don't have a problem with overachieving. We just have a problem with underachieving, which is why we want to minimize the total underachievement. So our new objective function for the goal programming problem would only include the negative deviation terms that we just defined. So now we have introduced our new decision variables, the deviation variables. We have formulated our objective function. Now we can move on to the constraint equation. So for this specific goal programming problem, our objective is to minimize the total underachievement of goals subject to the original constraints that we had initially for our LP problem, plus some additional constraints around the deviation variables, which we are going to add to create this LP problem as a GP problem. So the first four constraint equations that you see on the slide here are the equations that we created using our goals and the deviation variables. The first one is for total sales, the second one is for exterior door sales, the third one is for interior door sales, the fourth one is for commercial door sales, and the following three constraints are the ones that we had defined earlier for our original LP problem. So now we have two sets of constraints. The first one defining our deviation terms and how they're associated with the right-hand side values and our existing decision variables. And the second one, the original constraints from our LP problem. And obviously the non-negativity constraint that all of our decision variables must be greater than or equal to 0 or non-negative in other terms. In general, once we have defined all of our goals in a GP problem, the management should analyze each goal to see if it wishes to include only one or both of the deviation variables for that goal in the minimization objective function. In some cases, like I mentioned earlier, goals could even be just one-sided. So it's not even feasible to have two deviation variables. It's feasible to have only one deviation variable. But for this case, we have two deviation variables for each goal because it is possible to overachieve and underachieve the target. So in this case, for example, if Wilson specifies that the 180 target for total sales is an absolute minimum, then underachievement deviation variable can be eliminated from the GP model. So now that we have formulated the Wilson's GP model with the four goals, how do we solve it? There are two approaches that we can use in practice to solve this GP model that we just created. The first one is weighted goals. And in this video, we're going to do an example and solve for the weighted goals model. In the next video, we'll talk about the second approach, which is the ranked goal approach. So let's solve it as a weighted model. Now, as currently formulated, Wilson's GP model assumes that all four goals are equally important to its managers. That's because the objective function is just the sum of the four deviation variables. But if there is a case where one of the goals is more important than the other goals, then we can assign a higher weight to that particular goal, just so that we can tell the model that the achieving of this goal is more important than achieving the other three goals, which is why here we have set the weight for goal number 1 to 5 and the remaining three goals to 1. this gives us a new objective function, which is 5 dt negative plus dE negative plus dI negative plus dC negative. So notice that whatever weights we had assigned to each of these goals show up as objective function coefficients in your modified objective function. In summary, these weights can be used to distinguish between different goals. If the weights are not specified, it can be safe to assume that all the goals are equally important and your objective function is just the sum of all the negative deviations minus this 5 over here. We'd remove it if the goals were all of the same weight. But for now, because we are ranking goal number 1 as the highest of all the 3 goals and it's ranked much higher than the remaining 3 goals, we assign an objective coefficient of 5, which is the weight of this particular goal, to the deviation variable of that goal, which is dt negative. So now, using this weighted goals approach problem, what we've done is that we've reduced the problem to an LP model which has just a single objective function. Although we're solving for multiple goals, we only have one objective function which is going to go into solver. Let's switch to Excel to see how we can formulate this in Excel. So I've switched my screen to the Excel sheet and I've created sort of a template here which we're going to work off. Notice that this template is similar to the original LP problem that I showed you earlier. This part of the template, the exterior doors, interior doors, and commercial doors, is taken from the regular LP problem, as well as these three original constraints, which were in our original LP problem as well. So what I've done is I've added the deviation variables to my LP problem. These deviation variables, as defined earlier, are the negative and positive deviations for each of the 4 goals that we have. So now for our GP problem that we are solving, the decision variables would be this row, which I'm highlighting right now, just so that I can remember that these are the decision variables that are going to go into my solver window. Notice that in the regular LP problem, you only had 3 decision variables. Now we have 3 plus 8, 11 decision variables in total that are going to go in the solver window. The next line row item that I've added is for goal weights. This is the case if you're solving it as a weighted goal approach model, because you want to tell Excel that one or more of the goals are more important than the other goals. So since in the slides we had set this to 5, I'm going to put the weights of the other negative deviation variables under their column headings, so that I can tell Excel that goal number 1, which is the total sales goal, is 5 times more important than the other 3 goals. So now our objective function would be the sum product of these weights with our deviation variables. Notice that the original decision variables E, I, and C do not go into your objective function anymore. That's because we're going to add them as constraints in our GP model. So this cell here, M6, is going to serve as my new objective function, and I'll highlight this in green so that I can remember that when I move to the solver window. The next step is to put in the constraints that we added. I've already added the original constraints, the original 3 resource constraints that we had in our LP model. I'm only going to add the new 4 constraints, which were around the definition of each goal. The reason for adding these constraints to our model is so that Excel knows how each of these deviation variables are associated with the goals that we have. If we don't add these, Excel will not know that DT negative and DT positive are the total sales goal deviations, DE negative and DE positive are the exterior goal deviations, and so on. So that is why we have to add these 4 constraints, one for each goal in our goal programming model. The first goal is our total sales goal. So total sales is 70E plus 110I plus 110C. These are the selling prices taken from the input table that was given to us. Since DT positive and DT negative are the only 2 deviation variables which are associated with this goal, we're going to add coefficients for these into our model. So our first goal definition constraint would be 70E plus 110I plus 110C plus 1 times D negative T minus 1 times DT positive. The same way for the exterior goals, DE negative and DE positive are the deviation variables associated with it. So I'll put plus 1 for DE negative and minus 1 for DE positive. The same way for the third goal, which is interior doors, I'll put plus 1 for DI negative and negative 1 for DI positive. And finally, plus 1 for DC negative and minus 1 for DC positive. And here I'll put in this column M, I'll put the left-hand side values for our constraint equation, which would be the sum product of, I was supposed to start on the next row, row number 8. Yeah, sum product of this row with the decision variables row. And because the decision variables would remain constant, I'll put $signs in front of those references so that I can drag this formula down. And since these all contain formulas, I'm going to put blue color here, just so that I can remember that these zeros are a result of the formulas. And these are all equal constraints. For the goals, remember that the constraint equations would be equal constraints because by allowing the negative and positive deviation terms in, we are removing the need for inequalities. So everything would be equal for at least the goal constraints. The remaining constraints would remain the same as it is. I'm just talking about the goal constraints. And the right-hand side values here would be the goal targets that we have set. So 180,000 for total sales, 70,000 for exterior sales, 60,000 for interior, and 35,000 for commercial door sales. I'm sorry about the blue color, it's not matching here, so just to avoid any confusion, I'll just make it the same blue color. Okay, so now our model is complete in terms of all the input that we needed and all the functions that we needed to be in there. So we're going to move on to Solver. Before I open up the Solver window, as a part of the solution, I would like to know if by how much I overachieve and underachieved each goal. So to do that, I'm going to add some additional formulas in here in column P, just so that once I get the solution, I can also see which one of the goals am I achieving and which ones am I underachieving or overachieving. Just keep in mind that this additional step that I'm doing, just so that I can know which of the goals I've achieved and which ones I didn't achieve. This is not necessary for the solution. This is just a good to have. So the achieving goal number for each of these four goals would be the sum product of the selling price with the actual quantity that solver is going to give us. And so since the solver quantities are decision variables and it remains constant, I'll put dollar signs in front of those and drag this down. So this way, when solver gives me the solution, I will automatically know which one of these four goals I've achieved and which ones I have underachieved or overachieved. So now we can go to solve. The first input that we have to add to the solver is the objective function, which is the sum of all the negative deviations calculated in cell M6. We want to minimize that subject to the changing variables, which are these cells here in yellow. Notice that in our regular LP problem, we only had 3, but now we have 3 plus the 8 additional deviation variables, so a total of 11 decision variables in our goal programming model. Now I'll add the constraints. The first set of constraints are the ones with the equal sign. And then next set of constraints, which are from our original LP problem on resource availability. So now I've added everything that I need for the solver window to work. Hit solve. And looks like solver has found a solution for us. Here, what solver is suggesting is that we make 1,000 exterior doors, 800 interior doors, and 200 commercial doors. And looks like we have achieved 3 of our goals. The first 3 goals, we made a total sales of 180 exactly. So the deviation for that is 0, which is what you see under DT negative and DT positive. The second goal is also met exactly. So DE negative and DE positive are both 0 as well. The third goal, however, is overachieved because we had set the goal target to 60,000, but we have actually achieved 88,000, which is 28,000 more than what we had set. And that is why you see that the negative deviation for the third goal is 0, but the positive deviation is 2,800, which means that we have overachieved our goal by 28,000. And finally, goal number 4 has been unmet because we did not achieve our 35,000 goal. Instead, we underachieved it by 13,000 by making only 22,000 in revenue from commercial doors. However, this solution is still better than the original LP problem solution, where it was telling us to produce 0 commercial doors. At least now we know that we don't have to fire all of the salesmen in our company who sell commercial doors or who specialize in commercial doors.